Hello, and welcome back to our channel. Today we will be starting with our part 3 of Applied Physics 1. We will be looking at polarization. We'll be looking at the following contents in this video. Introduction to polarization. Polarization refers to the orientation of the oscillations of the electric field in a light wave. Light is an electromagnetic wave consisting of oscillating electric and magnetic fields. In unpolarized light, the electric field oscillates in all directions perpendicular to the direction of propagation. When light is polarized, the electric field oscillates in a specific direction or plane. Types of polarization. There are 3 types of polarization: plane linear polarization, circular polarization, and elliptical polarization. You can read about them in this slide. Polarization plays a crucial role in optics and is used in various applications such as reducing glare, in sunglasses, in photography, LCD displays, and in optical instruments like microscopes and polarimeters. Production of plane polarized light by different methods. Plane polarized light can be produced by several techniques, including absorption, reflection, refraction, and scattering. Polarization by absorption. This method involves using materials that allow light waves vibrating in a specific direction to pass through while absorbing light vibrating in other directions. Polaroid filters are the most common example. These filters consist of long-chain molecules aligned in a specific direction. When unpolarized light passes through the filter, only the light vibrating in a direction parallel to the molecular alignment is transmitted, producing plane polarized light. Polarization by reflection. When light is reflected from a surface, such as water or glass, the reflected light becomes partially polarized. The degree of polarization depends on the angle of incidence. Brewster's angle. At a particular angle of incidence, called Brewster's angle, the reflected light is completely plane polarized. Polarization by double refraction. Certain crystals, like calcite, exhibit a property known as double refraction, where an incoming light beam is split into 2 rays, the ordinary ray, O ray, and the extraordinary ray, E ray. These 2 rays travel at different speeds and are polarized in perpendicular directions. Nickel prism. A nickel prism is a device made from calcite used to produce plane polarized light. It works by allowing only the extraordinary ray to pass through while absorbing the ordinary ray, thereby producing polarized light. Polarization by scattering. When light passes through a medium with small particles like molecules in the atmosphere, it gets scattered. The scattered light, especially at 90 degrees from the incident beam, is plane polarized. This is why the sky appears blue and why polarized sunglasses are effective at reducing glare. Rayleigh scattering. This type of scattering explains the polarization of light in the atmosphere. The shorter wavelengths, blue light, scatter more effectively, leading to the polarization of scattered sunlight. Polarization by reflection and transmission through crystals. Quarter-wave and half-wave plates are used in optical instruments to alter the polarization state of light. By changing the phase difference between 2 perpendicular components of light, these plates can convert linearly polarized light into circularly or elliptically polarized light and vice versa. Brewster's law describes the condition under which light becomes fully polarized when reflected from a surface. The law relates the angle of incidence at which this happens, known as Brewster's angle or polarizing angle. Statement of Brewster's law. When light is incident at Brewster's angle on a surface separating 2 media, like air and glass, the reflected light is completely plane polarized, with the electric field oscillating perpendicular to the plane of incidence. Brewster's law is mathematically given by tan theta b equals n2 divided by n1, where Theta b is Brewster's angle. N1 is the refractive index of the first medium, typically in air, and 1 is nearly equal to 1. N2 is the refractive index of the second medium, example, glass, water. At Brewster's angle, the reflected and refracted light rays are perpendicular to each other, with the reflected light fully polarized in the plane parallel to the surface. A diagram for Brewster's law shows light striking a surface at Brewster's angle, with the reflected light fully polarized and the reflected and refracted rays making a 90 degrees angle to each other. Malus' law describes the relationship between the intensity of polarized light and the angle between the light's initial polarization direction and the axis of a polarizing filter. It applies to light that passes through a polarizer. Statement of Malus' law. When polarized light passes through a second polarizer, analyzer, the intensity of the transmitted light depends on the angle theta between the polarization direction of the light and the axis of the polarizer. Mathematical expression. Malus' law is given by I equal I naught cosine square theta, where I is the intensity of the transmitted light. I naught is the intensity of the incident polarized light. Theta is the angle between the polarization direction of the incident light and the axis of the polarizer. A diagram of Malus' law depicts a polarizing filter and an analyzer at an angle theta, showing how the intensity of light decreases as the angle increases. The transmitted intensity decreases in proportion to cosine square theta. Double refraction, also called birefringence, occurs when light enters an anisotropic crystal such as calcite, splitting into two rays, the ordinary ray, O ray, and the extraordinary ray, E ray. These two rays travel at different velocities and are polarized perpendicularly to each other. What is double refraction? In birefringent materials, light is split into two rays with different refractive indices. The ordinary ray, O ray, obeys Snell's law and travels with a constant velocity regardless of the direction. The extraordinary ray, E ray, does not obey Snell's law and its velocity depends on the direction of propagation relative to the crystal's optic axis. Both rays are polarized at right angles to each other. The O ray is polarized perpendicular to the optic axis. The E ray is polarized along the optic axis. Key features of double refraction. Birefringent crystals. Only certain crystals like calcite, quartz, and tourmaline exhibit double refraction. When unpolarized light passes through such a crystal, it splits into two rays, both traveling at different speeds and taking different paths. Nickel prism. A nickel prism is a device made from calcite used to produce plane polarized light by utilizing double refraction. It eliminates the ordinary ray and allows only the extraordinary ray to pass through, producing polarized light. Optical axis. The optic axis is the direction within the crystal along which light does not experience double refraction. In all other directions, the light splits into two rays. Mathematical expression. Double refraction leads to two refractive indices, and not for the ordinary ray, constant for all directions. And E for the extraordinary ray varies with direction. A diagram for double refraction shows light entering a birefringent crystal, splitting into two distinct rays, O ray and E ray, with different polarization directions and paths through the crystal. Quarter wave plate and half wave plate. Wave plates, or retarders, are optical devices made from birefringent materials that alter the polarization state of light. They introduce a phase difference between two orthogonal components of the electric field of the light wave. The most common types of wave plates are the quarter wave plate and the half wave plate. Quarter wave plate. A quarter wave plate introduces a phase difference of 90 degrees, or lambda by 4, between the two orthogonal components of the light wave. Working principle. When linearly polarized light passes through a quarter wave plate, the component of the light wave that is parallel to the optical axis of the wave plate travels at a different speed compared to the component perpendicular to the optical axis. This speed difference introduces a phase shift between the two components. Input will be linearly polarized light converts to elliptically or circularly polarized light depending on the angle between the polarization direction of the incoming light and the fast axis of the quarter wave plate. Application. If linearly polarized light enters at a 45 degrees angle to the optic axis of the quarter wave plate, it is converted into circularly polarized light. Conversely, circularly polarized light can be converted back into linearly polarized light when passing through a quarter wave plate. A diagram shows linearly polarized light entering the quarter wave plate and emerging as circularly polarized light. It could also show circularly polarized light passing through and becoming linearly polarized. Half-wave plate. A half-wave plate introduces a phase difference of 180 degrees, or lambda by 2, between the two orthogonal components of the light wave. Working principle. Like the quarter wave plate, the half-wave plate creates a phase difference between two components of the light wave, but the phase shift here is 180 degrees. This causes the polarization direction to rotate. Input will be linearly polarized light. The polarization plane of the light is rotated by an angle depending on the orientation of the light relative to the wave plate's axis. If the incident light is linearly polarized and enters at a 45 degrees angle to the fast axis of the half-wave plate, the polarization direction is rotated by 90 degrees. Key features include polarization rotation. The half-wave plate is typically used to rotate the plane of polarization of light. The angle of rotation depends on the angle between the light's initial polarization direction and the fast axis of the wave plate. It is commonly used in optical systems where changing the orientation of the polarization is necessary, such as in laser optics, polarimeters, and other polarization-sensitive instruments. A diagram of a half-wave plate shows linearly polarized light entering and exiting the plate, with the polarization direction rotated by a certain angle, such as 90 degrees. Nickel prism. A nickel prism is an optical device used to produce plane polarized light. It works based on the principle of double refraction, birefringence, in crystals like calcite. Nickel prisms are commonly used in optical experiments and devices where polarized light is needed. Construction. A nickel prism is constructed from a calcite crystal, which is a birefringent material. The crystal is cut at a precise angle and cemented together using Canada balsam, a transparent resin with a lower refractive index than calcite. The calcite crystal splits an incoming light beam into two rays, the ordinary ray, O ray, and the extraordinary ray, E ray. These rays are polarized perpendicular to each other. Working principle. The ordinary and extraordinary rays travel through the calcite crystal at different speeds due to double refraction, resulting in different refractive indices. The ordinary ray is totally internally reflected at the Canada balsam interface because its refractive index is higher than that of the balsam. The extraordinary ray, which has a lower refractive index, is transmitted through the prism. Since only the extraordinary ray passes through the prism, the light that emerges is plane polarized. Applications are that it is used in polarimeters to measure the optical activity of substances, incorporated in microscopes to improve contrast in specimens using polarized light, applied in optical instruments and photography, where polarized light is required. A diagram of a nickel prism shows the calcite crystal splitting the light into an ordinary ray, internally reflected and absorbed, and an extraordinary ray, transmitted. The extraordinary ray, which passes through, is polarized. Specific rotation. Specific rotation is a measure of a substance's ability to rotate the plane of polarized light. It is a fundamental property of optically active substances, which are capable of rotating the plane of polarization when polarized light passes through them. These substances include certain organic compounds, such as sugars and amino acids, that exhibit chirality, having non-superimposable mirror images. Definition. The specific rotation of a substance is defined as the observed angle of rotation of polarized light as it passes through a sample, normalized for concentration and path length. Mathematical expression. Specific rotation is given by this formula. Conditions for specific rotation. The specific rotation of a substance depends on the wavelength of light, usually the sodium D line at 589 nanometer, and the temperature. Key features. Positive specific rotation indicates that the substance rotates polarized light clockwise. Negative specific rotation indicates counterclockwise rotation. Applications. Specific rotation is widely used in chemical analysis to identify optically active compounds and to measure the concentration of such compounds in a solution, such as determining the purity of sugars in the food industry or analyzing the concentration of pharmaceuticals. Lorentz half-shade polarimeter. A Lorentz half-shade polarimeter is a device used to measure the optical rotation, or specific rotation, of optically active substances. It employs the principle of polarized light to determine how much the substance rotates the plane of polarized light. Working principle. In Lorentz polarimeter, the plane of polarized light is split into two halves by the half-shade plate. One half of the light passes through the transparent part, while the other passes through the optically active part of the plate. This results in two beams of light with slightly different polarizations. When no optically active substance is present, the two halves of the field, observed through the eyepiece, appear equally bright. However, when the sample is introduced, the plane of polarized light rotates, making one half of the field brighter than the other. By rotating the analyzer, nickel prism, the user can restore equal brightness to both halves of the field, and the angle of rotation is measured using the graduated scale. Construction involves the following. Light source. A monochromatic light source, often sodium vapor lamps emitting the D line at 589 nanometers, is used to provide polarized light. Polarizer. A polarizer, such as a nickel prism, is placed in the path of the light to produce plain polarized light. Half-shade device. Lorentz polarimeter uses a half-shade plate. This plate consists of two halves, one transparent, and the other half having a small optical rotation. This creates two beams with slightly different intensities when viewed through the analyzer. Sample tube. A glass tube holds the solution of the optically active substance. The length of the tube is known and can be varied. Analyzer. Another nickel prism is placed after the sample tube, which is used to analyze the light emerging from the sample. Eyepiece. The user observes the light through the eyepiece to measure the rotation angle. Key features. The half-shade plate helps in achieving higher precision by creating a difference in brightness, making it easier to detect small changes in the plane of polarization. Accuracy. Lorentz polarimeter is more precise than standard polarimeters because of its sensitivity to small differences in brightness between the two halves of the field. Steps to measure specific rotation. Fill the sample tube with the optically active substance. Example, a sugar solution. Place the sample tube between the polarizer and the analyzer. Adjust the analyzer until the brightness of both halves of the field in the eyepiece is the same. Record the angle of rotation and use the formula for specific rotation to calculate. A diagram of Lorentz half-shade polarimeter illustrates the following components: the light source, polarizer, half-shade plate, with transparent and optical rotation sections, sample tube, analyzer, and eyepiece. The diagram would show the polarization state of the light as it passes through these components and how it is analyzed by the user. Now, let's revise what we studied in this quick summary. Polarization refers to the orientation of the electric field oscillations in a light wave. In polarized light, the oscillations occur in a specific direction or plane. Plain polarized light can be produced using various methods: absorption, reflection, double refraction, and scattering. Each of these methods has its own unique applications, from reducing glare in sunglasses to being used in scientific equipment for analyzing optical properties. Brewster's law explains the angle at which light reflected from a surface becomes completely polarized. This angle is called Brewster's angle, and it's used in photography and optics to reduce glare and improve visibility. Malus' law describes the relationship between the intensity of transmitted polarized light and the angle between the incident light's polarization direction and the axis of the polarizer. It's essential for understanding how polarizing filters work. Double refraction, birefringence, occurs in certain crystals where light splits into two polarized rays, each with different refractive indices. This phenomenon is used in optical devices like nickel prisms to produce polarized light. Quarter wave plate introduces a 90 degrees phase difference between two perpendicular components of light, converting linearly polarized light into circularly polarized light or vice versa. Commonly used in 3D technology and optical instruments. Half-wave plate introduces a 180 degrees phase difference between components of light, rotating the polarization direction of linearly polarized light. Used in applications where polarization direction control is needed. Nickel prism, a device made from a calcite crystal that produces plane polarized light by splitting an incident light beam into two rays, ordinary and extraordinary, with only the extraordinary ray transmitted. Widely used in polarizing devices and optical experiments. Specific rotation is a property of optically active substances that describes how much they rotate the plane of polarized light. It is influenced by the concentration of the substance, the length of the sample tube, the wavelength of light, and the temperature. Lorentz half-shade polarimeter is an instrument designed to measure the optical rotation of substances with high precision. It uses a half-shade plate to create a difference in brightness in the two halves of the field of view, allowing for accurate detection of small rotation angles in optically active samples. And with this, we wrap up our video on polarization. I hope you liked it, so please like, subscribe, and comment, and see you in the next video.